Alright, so here we have the lemniscate graph
To infinity and a defined amount of undefined values.
by Ricky Traub, Harry Gibbons, and Thomas Krasinski.
Doo-doo.
So in this equation we have three variables. We have r, which equals the radius and is always positive. We have a, which is the x-intercepts of the cosine function, or controls the maximum deviation from the origin of the sine function or negative cosine function. We also have theta, which is the input of the function and can stand for either degrees or radians. So here we have the rectangular coordinate plane graph of the cosine. Here it's in radians, and you can clearly see where the undefined regions of the graph are. In this graph, when the a value is changed, the humps of the graph are increased. And here we have the rectangular coordinate plane graph of the sine function. Here it's pretty much the same thing as cosine. It's in radians, and the only difference is that it's shifted over 45 degrees or pi over 4. But again, if you change the a value, the humps become larger, and that's pretty much it. Here we have the parent polar graphs of cosine. It looks like an infinity graph, and what the variable a does is that it shows the farthest point from the origin, or the max radius, which also end up being on the cosine graph the x-intercepts. So here we see the parent polar graph for sine. It's the same shape of cosine, it's just rotated. Again, the a value shows where the max deviation from the origin is. Here we see the data table for the parent graphs of cosine right here. It's important to point out that after 45 degrees, the values of r become undefined. This is because the coefficient of theta in this equation is 2, and so after 45 degrees, the values of cosine become negative, and you cannot have the square root of a negative number. It's also important to point out that after 180, the values repeat because of the 2, and it'd be like having another period. Right? Here is the data tables for the parent graph of sine. It's pretty much the same thing as cosine, except the undefined locations are between 90 and 180 here. And these values are undefined because after 90 multiplied by 2, that'd be 180. So for sine, that anything after 90 would become a negative number. So again, it'd be a negative square root, and that's not possible. So here we have the variations of the a value. When a in a cosine Lemniscate equation is 2, that increases the maximum distance from the origin from 1 to 2. In the equation you can see that it is not 2, but in 4, but this is because the original equation is a squared, so here we just simplified it to equal 4. So here we have the variations of the a value in the sine function. Again, it does the same thing. It increases the maximum distance from the origin. Again, you can see that's 4 because of the original equation, a squared sine 2 theta, except in here we had to use t for the Graphmatica. So here we're learning how to graph the given equation. Here we're going to have the example given a equals 3, graph the sine and cosine Lemniscate graphs. The equation for these functions would be r equals the square root of 3 squared cosine 2 theta, which would end up coming out to r equals the square root of 9 cosine 2 theta. In order to graph this, since a equals 3, we know that is the max deviation from the origin, and because it's a cosine graph, it'd be on the x-axis. In order to graph the other points, it's easiest to just plug them in the equation and figure them out that way. and yeah, then we have the lines going through the origin in the center, all meeting up, coming out to this shape. So in this graph, you can also see where the undefined portions of the area are. They're not quite as easy to see as when it's in the rectangular graph, but they are visible in between the two circles of the graph. Alright, so here's the sine graph. Again, the A equals 3, so that'd be the max deviation from the origin. And here we graph that deviation on the 45-degree line because it is shifted by 45 degrees. We plugged in the points in order to get the graph. And again, the lines come together at the origin, showing where the undefined points are in between the two circles. Alright, so in this slide we're going to do the opposite. We're going to write the equation given the graph. So previously learned, we knew that A was the max deviation from the origin, and so from this graph we can see that A would equal 3, and we would plug that into the equation over on the side, and it would come out to R equals the square root of 3 squared cosine 2 theta. However, we see that this graph is different from the others. It is vertical, which means that A is negative. And when A is negative, instead of being the x-intercepts, it is the y-intercepts. And from this point forward, we would simplify. So it would come out to R equals negative 9 cosine 2 theta. Oh, excuse me. It'd be the square root of 9, negative 9 cosine 2 theta. There we go. Alright, so in a sine graph, it's the same process that we use. You look at the farthest point away from the origin, and that becomes the A. You plug it in. When the A value is negative in a sine graph, however, it is flipped over the y-axis. So instead, yeah, there you go. So instead of going from low to high, it goes from high to low. If you can sort of see where that is. But yeah, it starts from up there, yeah, and goes down. There you go. But yeah, we have a few problems for you guys to try in class. The answers are on the back, and gonna pass that out for you guys to try out. So have a nice day, and we'll see you in class.